We've spoken about how IP addresses are used, but not where they come from. Who assigns them and who decides who gets which address? Your address on the public internet is assigned to you by your ISP. When your home router authenticates with your ISP's access node, part of its housekeeping is to ask your ISP to assign you an IP address. While you can pay to have a fixed one, typically your ISP assigns you an IP address at random from an available pool. I say you, it's your home router that's assigned the IP, not the individual hosts on your home network. Although if you're out and about, your smartphone will be given its own IP by pretty much the same process. But if it's your router that's assigned an IP address, what about the devices on your home network? Your router handles this assignment, also picking the addresses from an available pool of private network addresses. These are ranges of IP addresses earmarked for this exact purpose, private networks that aren't visible to the public internet. If you ever wondered why you always see addresses beginning with 192.168, this is why. Your router knows that these addresses are safe to use. And if you try sending a packet to one of these addresses, core routers on the public internet will just ignore it. But wait, if the devices on your home network have completely different addresses to what your router's been assigned, how does traffic from a server ever find its way back to your device? Surely it would be unroutable. Never mind the fact that presumably everyone else's home network is using the same set of IP addresses. When your packets pass through your home router on the way to the internet, they undergo something called network address translation. This is where your router swaps the sender address on a packet for its own, and makes a note of having done this. When the packet goes out, it's seen as coming from your home router, which does have a public internet address, so any responses to outgoing packets are sent back to it. And when those responses arrive at your home router, the swap happens in reverse, where the responding packet's destination IP is replaced with that of the host on your home network that originally sent for it. Imagine mailing somebody in a large office. You probably don't know the exact desk where they're sitting, but that doesn't matter. You just need to get your packet to the mailing room and they'll sort it from there. Equally, when the company sends things out, they're not putting exact desk numbers on their outgoing mail either. So your ISP, or more precisely your ISP's border network gateway, assigns your router an IP address from a pool of addresses that it's been assigned. But who assigns addresses to the assigner? The internet isn't governed by one single organisation, but rather several different organisations that variously provide oversight, technical standardisation, and a forum to facilitate discussion and coordinate efforts. This between the aforementioned groups as well as governments and other organisations. There's a long history to these groups I'm not going to cover here, but in terms of IP addresses, the relevant ones are the Internet Corporation for Assigned Names and Numbers, otherwise known as ICANN, its child organisation, the Internet Assigned Numbers Authority, otherwise known as IANA, and the world's regional Internet registries. ICANN is the body in charge of approving and allocating IP addresses on the public internet, as well as autonomous system IDs and indeed the website addresses themselves. In practice though, what ICANN actually does is sets the policy around how this is done. It's IANA that's responsible for the actual allocation. IP addresses are doled out by IANA allocating blocks of unused addresses to the world's 5 regional internet registries. These registries in turn allocate blocks to local internet registries, ISPs or other organisations that desire them, and from that pool of addresses, your ISP picks one and gives it to you. Surely there's a limit to this though. IP addresses have 32 bits, which mean you can only represent about 4 billion addresses. Obviously that's a big number, but there's a lot of people connected to the internet, and a lot more connected devices. Wouldn't we run out one day? There's actually a name for this, IP address exhaustion, and it's long since already happened. The internet as we know it was developed well before smartphones and tablets, and even still before personal computing had really taken off. At the time, 4 billion seemed a very far off ceiling, but on the 31st of January 2011, IANA officially ran out of IP blocks to assign to regional registries. In April of that year, the Asia Pacific Network Information Centre became the first regional registry to run out of IP addresses, and of course, be unable to request new ones from IANA. Fortunately, IP exhaustion was identified as early as the late 1980s, so there's been a lot of work to prepare for it, which is why you can still use the internet today. Going back to the internet's governance, this is what organisations supported by the Internet Society do. It was the Internet Engineering Task Force, supported by the Internet Research Task Force and overseen by the Internet Architecture Board, that proposed the solutions to IP address exhaustion. In particular, the network address translation we saw earlier, allowing a single IP address to effectively represent an entire private network, and allowing subnet masks to be of variable length, allowing more addresses to be squeezed from the same block. The real resolution, though, was to create a new type of IP address. The addresses we've seen so far are IPv4 addresses, but in 1998 the IETF defined IP version 6. If you're wondering what happened to IP's version 1, 2 and 3, these were all experimental protocols created when the internet was developed, but ultimately abandoned. IP5 technically exists, but it's better known as Internet Stream Protocol, which is also experimental, and was never actually used. So IP version 6 was picked, just to avoid any confusion. Version 6 addresses work in pretty much the same way as version 4's, except they use 128 bits instead of 32, have prefix lengths instead of subnet masks, and their shorthand is 8 groups of 16 bits called hextets instead of 4 groups of 8 bits called octets. All IP4 addresses are valid IP6 addresses, and almost all modern equipment is IP6 compatible. In theory at least. This was put to the test 5 months after IANA ran out of IP version 4 addresses. On the 8th of June 2011, the Internet Society hosted World IP version 6 Day, where 400 of the world's most prominent internet and technology companies set their equipment to only use IP version 6 for the day. Fortunately, it was a success, so much so that a year on, World IP6 Launch Day took place, where IP6 was enabled alongside version 4 for good. Hang on, so we've added a few more bits, is that really going to fix everything? I mean, 128 is only 4 times longer than 32, isn't it? It is, but remember, each extra bit we're adding doubles the number that we can represent. So, if 32 bits can represent 4 billion addresses, 128 bits can represent 340 underkillion, 282 decillion, 366 nonillion, 920 octillion, 938 septillion, 463 sextillion, 463 quintillion, 374 quadrillion, 607 trillion, 431 billion, 768 million, 211,456. In case you were wondering, that took 20 seconds to pronounce. To give you some context as to how much bigger that is, if the version 6 address space was the Pacific Ocean, the version 4 address wouldn't even be the size of a teardrop. So it's reasonable to assume we're not going to run out of version 6 addresses anytime soon. In summary, the internet is governed by a number of organisations, such as ICANN and IANA, who administer the IP address space, and the IETF, who along with the ITU and the IEEE, as I mentioned in part 2, maintain and set technical standards. This means that ICANN are, ultimately, the ones who assign you the IP address that you use on the public internet. Not directly, mind. ICANN delegate this to IANA, who assign blocks of IP addresses to the regional internet registries, who in turn assign them to ISPs, who themselves in turn pick one out and assign it to you. The IP addresses we use used to be what's called IP version 4 addresses. These are 32 bits long and written as 4 octets. You can only represent 4 billion numbers with 32 bits though. While that's certainly a lot, there's many more devices than that in the world, so it's perhaps unsurprising that in 2011 IANA ran out of IP version 4 addresses to assign. Fortunately, this was seen a mile off, so the world was prepared, with the IETF proposing a number of solutions, like network address translation and classless inter-domain routing, both of which helped to eke out some extra mileage. But the real fix was IP version 6 addresses. Version 6's 128 bits against version 4's 32 meant that rather than clever recycling techniques, the fix was to just not run out at all. In fact, if you divvied up all the possible IP version 6 addresses, and did so evenly between every human currently alive on Earth, each person would individually have more IP addresses at their disposal than there are stars in the observable universe. Hopefully that'll fix the problem of running out,